We'll start with something called a sparse matrix. In fact, you must have you must have got even in Gauss elimination method and all. There's something, the matrix becomes a diagonal matrix. Okay, and this is and the sparse matrix is something a very challenging thing in the in this field, because you don't know because you will get something like a 500 by 500 cross matrix. Okay, and if you see the 500 by 500 cross matrix, most of the elements will be 0. Hardly some few diagonal elements or sum of diagonal elements will be the valid number, will be the real number. Otherwise, all the other elements are going to be 0. So if you actually, when you are solving it, if you actually store the entire zeros, you are unnecessarily using a memory locations. Okay, and this is going to be very serious. In all the numerical, you will see most in the HUD also, as you go along, you will see you get many matrices, and all these matrices are typically sparse matrices. Okay, so one of the important class of sparse matrix is what we call is a tridiagonal matrix. Okay, so what is this tridiagonal matrix? So the tridiagonal matrix is something. You have the 3 diagonal elements and the rest of the elements all are 0. Okay, and there are other matrices also. You get something what we call as a band diagonal matrix. You must have heard of it. This is a tridiagonal matrix where above and below all elements are 0. Okay, so in the band diagonal matrix you have a certain number of diagonal elements above, say M1 or M above will be non-zero. Similarly, from here some n diagonal elements will be non-zeros, rest of the elements all will be zeros. Okay, so these types of matrices you encounter in your numerical methods quite often. Okay, so and how we are going to do this such a kind of matrices, it's a very at times tricky and maybe a challenging at times how we are going to store this matrix and everything. So here today we will see a simple sparse matrix. It's a simple tridiagonal matrix, and we will see how to solve it without storing the zeros. Okay, and I want all of you to write this code to solve this tridiagonal matrix without storing the off diagonal elements, because in the later on in all our, as we go along, we will be using this particular routine. Whatever the routine your module you develop, we'll use this very extensively. Okay, so if you submit it, I'll put it up in your folder and I can just pick it up from your folder in all our later programs. Okay, you don't have to really send me again and again. Okay, so that's why you can use it. Okay, so the way how this tridiagonal matrix are stored is, you basically the idea is if I try to rotate this matrix something like this, so then it will become become a combination of 3 vectors. Am I right? I can store it like this. Okay, so this is the way you store. If I store this tridiagonal matrix like this, then what happens? Then I can I don't really save much of zeros except this first and the last element. I have to keep it up, but anyway, this will not be used in your calculation. Okay, so that is the only element I will be using, and rest of the elements will not be rest of the zeros I will not save it. So this is the way. Now since you have deformed, so this is basically deformed matrix. Okay, since it is deformed, so your matrix multiplication, what is that we are having? A dot x, that's what we are doing, right? Equal to b, or a dot x equal to b. This is a matrix multiplication we are doing. So this entire algorithm itself has to be modified. You got it? Am I clear, everyone?
Yes, sir.
So you have to modify this algorithm itself. So, and how we are going to do it? This algorithm I am not going to give you right now. I want you people to think. Okay, it is not very tough. Once you start, take it up. I want you to develop this algorithm. Take a pen and a paper. sit and see how we are going to do it out. So the idea is, first storing a trigonal matrix is simple. That's why this way you can store it off. Okay, you can store this matrix like in this form. You can store it, and now the challenge means, okay, the trick is how we are going to solve this equation. Okay, so yeah, hello. Yeah. So how we are going to solve this equation? Fine. And okay, I will give you the point is, I can give you a technique. You can actually use LU decomposition also, but if you use LU decomposition, there is a chance many of these zero elements will eventually become non-zeros. Okay, and then you have to store those elements also. But it's not always happen. Many times you can handle it, except not making all the, you may have to possibly extend the diagonal elements a bit, not completely. We have to store all the matrices. Okay, so that's what the challenge is. The sparse matrix keeps changing. But what I can say is the more simpler method is a Gauss elimination. So all you have to do is you have to convert them into diagonal element, right? So you have to convert this off diagonal element into zeros. So use your row manipulation and convert this off diagonal elements into 0. Okay, and then you can actually then you can solve by using your backward substitution. Okay, the way we used to do in the earlier one. Okay, but only thing is you will be not using the zeros. You will be using only the three diagonal elements. Okay, it is not tough, and I can tell you even Gauss elimination is okay for a tri-diagonal matrix, because you are not going to do really too many operations. Every row will involve only 3 operations. Can you see? Can you people see it? Hello? Am I right?
So some of these tri-diagonal elements can also be zeros, right?
Oh yeah, that you can. Yeah. That's what I'm saying. See, there are. I'm not going into that detail of it. There are times what happen. There's a matrix I can draw and show something like that. You get a matrix, something called as. We will encounter that matrix also. We have certain diagonal elements. Okay, certain diagonal elements, and then what happened? Then you will have a sum of diagonal elements, something like this. This matrix we will encounter during our course. Okay, so something like that. You can draw all sorts of, but it have a pattern. You got it? So this type of matrix. So these are all non-zeros, and rest of all the elements will be, all the other elements will be zeros. So this what they call is a, I think if it is a diagonal matrix with fringes. They have a name for these names. Okay, and you are right. Sometimes you may get a matrix something like this also, as you are said. So if you get a matrix something like this, and then there will be a 0, and then there will be some matrix like this. Am I right? This is what you are telling. Am I right? Hello? Yeah.
Yes, sir, got it.
Yeah. So that's what I'm saying. For all these matrices, this is a one simple example I have taken as a tri-diagonal matrix. Why I am doing this tri-diagonal matrices? This is what we will face very often during our numerical technique when you are approaching. But yes, sometimes when you are using for a more involved problem, you may get a combination something like this. These are all non-zeros. I write a square as non-zeros. These are zeros. So then what happens here also? You are not supposed to save all the elements. There can be a matrix like this. You got it? And rest of all the elements will be zeros. Okay, so then you are supposed to store only these elements. Okay, and then you have to define your entire algorithm based on this. And even I will tell you, even you are defining it, even your operation should not involve these zeros. If you want to involve zeros, that means of course you already store them in an array. Am I right? So that is the catch here. So you have to store only these elements, and you have to, here this is more complex. I don't go into this one. So if at all, if you are lucky, you will end up such matrices and you will get a good algorithm to develop. That's good. But in most of your cases, I can say what you will commonly face is this tri-diagonal matrix. That you will see in as we go along the course, you will face this tri-diagonal matrix very much. Okay, say from interpolation to or whatever you can. So
initially when we're taking the input,
yeah.
when we're reading the file or when we're taking the input, at that time the zeros will be stored, no? To check whether it's a tridiagonal matrix or not.
Correct. So the point is, see, that's what you normally we don't write a matrix. Your matrix solving program is not like an independent matrix solving program. It will come as a module in your program. So your program will eventually develop some matrices, and that matrices to be solved. That's why I said other day in the pivoting also. When I give you the matrix, when I ask you to solve the matrix, when you can see the matrix, you can actually pick up. Okay, well, you can always work around and make it without pivoting. Also, you can do it. Okay, so often all the time the matrix solver will be inbuilt in your program. Okay, and whether the problem what you are going to handle, that's why I said when we will see later on a spline interpolation. Okay, we will go into the interpolations also, or if you are going a partial differential equation, you are solving a Poisson's equation. All these equations, okay, will eventually give rise to a matrix, which will be sparse matrix. Most of the cases it will be tridiagonal, and if you are either you call lucky or unlucky, then you will get a matrix like this, tridiagonal with what do you call tridiagonal with fringes. You will get a matrix like this. Okay, and most of the times you will get these are the matrix. So what happens? Beforehand itself, you know, when you are developing the algorithm to solve a particular problem, you know that the matrix what you are going to get is either tridiagonal or diagonal, means whatever fringes or whatever the matrices. So then you don't provide the zeros. That's the point I want to say. You normally don't provide the zeros. Your program will provide only this element. You don't really have to bother about the zeros. You are not reading a matrix there. Am I making it clear?
Okay.
So you will not when you as you go along, you will see you will not produce a matrix. You will not store a matrix at all. What you will store is only these diagonal elements. Okay, and that is what you have to solve it. Am I making it clear now?
Yes, sir.
Yeah. Okay, so fine. This is the what we will means. Okay, and yeah. So now this this matrix even since we are so you can see very well here itself. So you are not going to really do a lot many operations. Every row only have 3 operations. Am I right? 3 additions, because you have to just multiply only these 3. Only these certain 3 elements will be multiplied and then can be equated with the b. So you don't really do many operations. In fact, you can even use your normal Gauss elimination. Okay, where you make one of these off diagonal elements 0, and that makes its what you call upper triangular matrix, or means again it is a diagonal matrix only. So only these 2 elements will survive. Okay, I can show you in Gauss. If you try to do Gauss elimination, you can maintain all the zeros and you can still convert this element to 0, and you have only these 2. Am I making it clear? Think of, when you do algorithm, you will see you will get only these 2, and this is not very tough. Whatever the algorithm you have developed already for Gauss elimination, you can actually use the same algorithm. It will be same thing. Only the loops will cut down to 3. Okay, because you're going to two operations here. Okay, so and this is what we will use for it. And okay, well, one of the important thing is, of course, in the tridag also you will have something, the problem of pivoting. You understand? Because of course here also, if you divide it with the b. Sorry, I have used the same term. I forgot. I should have used some different term here. Let me call it as b. Okay. So what will I call? I should call it as d here. Better I will call it d. Okay? I didn't realize it. Fine. So yeah. So what happened is your diagonal elements. So the diagonal elements here also you should always make a check which is not equal to 0. You will see when you develop. Again you will always divide by the diagonal element. Otherwise you will not able to solve it. So you should always have a check the diagonal element should not go to 0. We won't involve pivoting in a tridag for a simple reason. The moment if I want to use a pivoting, can you tell me why we don't involve pivoting in a tridag? Can anyone tell me the reason? Can anyone tell me? By using pivoting, we are killing the whole.
Then they should remain tridiagonal.
Yes, exactly. Don't remain tridiagonal. Okay. Then your whole, if you start pivoting, then you have to store all the zeros because you have to really make all this row swapping and column swapping. And of course, even some elements will come here, 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 and all. Okay. So you can't maintain the tridiagonal form. So that's why in a tridag, when you are solving tridag, you don't normally do the pivoting part. You shouldn't, because you have to store all the zeros also. Okay, you shouldn't use the pivoting part. Now the question comes, yes, then your tridag is always prone to that divided by 0. So your tridag routine, the moment when you are making a tridag routine, that should always, for every cases, it should check this condition. You got it? And only thing I can tell you, most of the problems which gives rise to tridag will be always something called as diagonally dominant. You know the meaning of the word of diagonally dominant? So the diagonally dominant is, suppose if you have this matrix element, suppose if this is the one, I have a matrix A. Okay, the diagonally dominant is something like your A of II is mod. Sorry. Okay, I should do it like this. So A of II mod should be greater than summation of I equal to, j equal to 1 to n, and j is not equal to I, and this will be A of ij. You got it? Sorry, mod, I would write it as a mod. Can you understand? Are you able to clear what I'm saying? So this condition is called as your diagonally dominant matrix. Okay. So most of your cases, what you will encounter will be a diagonally dominant matrix. Okay. So and if your matrix is diagonally dominant, then you will never face this problem of pivoting part. Okay, so it will always be diagonally dominant, and you don't have to use a pivoting. Okay, so all you can do is you can probably at times, sometimes you may have to reframe your problem such that it will make you always diagonally dominant. But yes, in case of tridag, most of the cases when you use tridag, you won't actually face this problem at all, because they will be usually diagonally dominant. Okay, am I making it clear?
Yes, sir. Sir, but can we do pivoting in deformed matrix?
That's why I'm saying, yes, if you want to do a pivoting in this deformed matrix, the moment if you do, then your off diagonal elements will take, some of the elements will move to off diagonal. Correct?
Sir, you have written matrix below this, not deformed matrix, where you have rotated it.
Here. Correct. You are
Yes,
right. You can think of the answer. So this matrix is not the real matrix. This matrix is basically this. Am I right? So the moment if I do pivoting, when I swap this row swapping, say something like, for example, this column I am swapping with this column. So then this guy will come. So then this element, okay, I have made a lot of, well, let me try to remove some of these guys. What do I do? Fine, yes. One moment, let me remove this. Oops. Okay, so for example, let us take an example of I am going to swap this row with this column and this column. Okay, let us take it. So then, because this column is swapped, this element is not these two elements will not be, this will become non-zero, whereas here from this element will become, will not be zeros. Am I right? These elements will have non-zeros. So now you see, as I keep swapping, and then if I do some row swapping also, so then again the same thing. Am I right? So when I do the row swapping, so these three elements will not become will not be zero anymore, and similarly these two elements will not be zero anymore. So what I want to say is, the moment if you do the pivoting part, so then this matrix, what we wrote this matrix, sorry. All right. Okay. Fine. I guess this I can't help it. Fine. Yeah. So right. So what I want to tell you is, so the moment when you do this pivoting part, so this matrices will start growing along the. This will start growing. Got it? Can you understand? Clear? Huh?
Yes, sir.
Yeah, so this will start growing from both the directions. So then eventually it doesn't make any purpose for you to save this matrix at all. Okay, so that's the reason in Tridag we don't implement pivoting. Okay, and you don't have to. That's what I'm saying. Means most of the times it will not be required, Tridag. Okay, your diagonal elements will not be zero. Okay, the moment if you have a problem with the diagonal element 0, then that problem itself is an ill-post. Okay, so and then your x vector should not be. That's what I wrote some of the. Okay, I removed that. Some of the way where I think someone was asking what happened if some of the diagonal elements is 0, right? So then what happened for particular that element, that solution you can't find it out. You have to remove that solution and reframe your problem accordingly. Okay. And this is all doable. When you really do into the research and when you are finding the problem, these are all the techniques you can actually do. Okay? Clear, everyone?
Okay, sir.
Yeah. So this is the way a tridiagonal matrix has to be solved, and this assignment also I will send you, and everyone do this tridiagonal matrix. Okay? It is very simple. If you have done the Gauss elimination, you can use the same Gauss elimination, and it doesn't matter. You don't really go for using for LU or something like complex. That's okay. Okay, because when you do Kraut's algorithm, sometimes the off diagonal element also becomes the zero elements also will become taken finite value. So anyway, we know Gauss elimination. In Gauss elimination, I can show you only, you can make only this diagonal off diagonal element to be 0. That is this. Okay, I should use this one. So only this off diagonal element can be make it 0. Okay. So if you want, sometime I can give you a demo. It's up to you. Okay. If you people want me to give a demo for that, how to make this solve a tridiagonal matrix, I can give you on some later classes or maybe at extra time. Okay. Cool, everyone.
Yes, sir.
Okay.
Yes, sir.
Yeah. So and with that I stop this matrix solution by elimination methods. Okay.